superimposable mirror images of each other. Now, how can you distinguish them? I said most of the time, unless you're talking about a biological reaction, most of the time the two isomers react in identical ways. Right, now the way you distinguish them is by using polarized light, okay? And if you do physics, you might know what polarized light is already, but if you don't, you probably don't. Right, so what you've got here, right here, I've got a, right, that's going to be a water wave, yeah? And that is on this axis here, you have got, that's the displacement, yeah? And on this axis here, you've got the progress, and the water wave is moving in this direction, okay? And as we know, it's a transverse wave, light behaves in a very similar way to that. Now, if you just think about your, if you've got a little water molecule there, do it in green, then effectively that water molecule is going to be going up and down as the wave passes in this direction, isn't it? Okay, and so what I've shown here, right, is we are looking at light. Now imagine you're in the middle there, and you're moving the direction with the light wave. Now the vibrations can be up or down. Okay, can be up or down like that. So horizontal, vertical, or they could be in this direction, or some of them could be in that direction, or that there, okay, or any other angle which I can't draw in there because it'd be too messy. Okay, so this is what normal light is like. So light made by a light bulb is like this. So what we've got here is, right down here is a light bulb, and we've got vibrations in every possible at every possible angle, okay? All the vibrations. Now, the light from here is going to go through a filter called a polarizing. It is a polarizing filter. And if you get some sunglasses, or like Polaroid sunglasses, the filters they have in it are actually polarizing filter. Now, once the light has gone through the polarizing filter, it cuts down all of the directions of vibration of the light waves, except for one. It just allows one direction of vibration. So I've drawn the ones there being in the up and down, in the vertical. Okay, so this light wave is now passing through the polarizing filter. Now what I've got in this test tube here is I've got one optical isomer of a compound which is chiral. Now when it is passed through that, you will see what happens is the light is polarized still, but the plane of polarization has been rotated. Okay, so I'll write that down there. The plane of polarization has been rotated. Now, if the molecule is doesn't exist as two optical isomers, that won't happen. If you have a mixture of the two optical isomers, then you won't notice the plane changing there, because what happens is one isomer will rotate the plane in a clockwise direction, okay, and the other isomer will rotate the plane of polarization in the opposite direction. So that's how you can distinguish between the two isomers. One turns it one way, one turns it the other. Okay, that is how you determine which isomer you've got. You shine polarized light through it, through the sample, and you look at how the plane of polarization has been rotated. Now, don't worry how you do that. You don't really, at most you're going to get a 2-mark question on that, but you can quite easily tell how the plane of polarization has been changed. Right, just now a few little jargon words. So there, what we'd say is, right? Then you might see something like the product of the reaction is optically active. What does that mean? Well, it means, in other words, it rotates the plane of polarization. So that means it contains one isomer of a molecule with a chiral carbon. Chiral carbon being an asymmetric one. Now, if a solution is optically inactive, and this is where it can cause a bit of confusion here, it can mean one of two things, okay? It can mean, one, that the compound has no asymmetric carbon in it, or it can mean that you have a 50-50 mixture of two optical isomers of the same compound. Okay, and what with this is why doesn't that change the plane of polarization? Well, that relates to here. One lot of molecules are going to rotate it one way, one lot are going to rotate the other way by an equal amount, so there's no observable difference. Okay, now this 50-50 mixture, and we'll come to this term again, it's got another jargon word. It's called a racemic mixture. So a racemic mixture is when you have a 50-50 mixture of two optical isomers, two non-superimposable mirror images of each other. Okay, so I think we'll leave that there.